Welcome to a brand new episode in the Science and Technology Unleashed series. My name is Anila and I am going to be your host for this episode. Mona Hazar-Imam has said, if the frontiers of physics are changing, it is due to scientists discovering more and more about the universe, even though they will never be able to probe its totality, since Allah's creation is limitless and continuous. Join us as we explore how our universe came to be and function through the lens of astrophysics. Our first guest is Dr. Rf Babul, an internationally renowned astrophysicist and distinguished professor at the University of Victoria in Canada. He has made a number of contributions in the field of physical cosmology and is a recipient of several prestigious fellowships, including a Neuroscience Fellowship at the University of Cambridge and Liverham Visiting Professorship at the Universities of Durham and Oxford.
My name is Rf Babul. I'm a University Distinguished Professor at the University of Victoria in Victoria, British Columbia, Canada, and I'm an astrophysicist. Astrophysicists study everything from the very beginning of the universe, the birthing of space, the origin of time, matter and energy. Everything that we see in the universe was created in this event that we call the Big Bang. And then over the course of nearly 14 billion years, the universe expanded, the matter got organized in different fashions, galaxies formed. From inside galaxies, you had stars forming, and around stars, you have planets forming. That whole scope, literally, 14 billion years of the universe's history, that's what astrophysicists study. I focus in on the organization of matter. In other words, when the universe came out of the Big Bang, it was incredibly smooth. Think of a really still surface of a lake. Very, very fine ripples present, no bigger than your hair's width. And from those ripples emerged galaxies. And within the galaxies, stars formed. And at the centers of these galaxies, we have these black holes that are 1 billion times the mass of our own sun. How did all this happen? What physics shaped the universe? These are the questions that astrophysicists answer, and these are the things that I work on. I can't go back and redo the Big Bang. That's physically impossible. But we use some of the most powerful supercomputers in the world. We code up our understanding of the science at present, knowing that we're missing a lot. We then let the computer run and recreate the Big Bang and the 14 billion history of the universe. We see what comes out. We try and play detective. We play, we change. Our colleagues are looking at the universe, they're coming up with clues. We are trying to reconstruct the history of the universe. We're trying to reconstruct the very laws and the very physical processes that shape the universe. Let me just mention that three of my colleagues, Roger Penrose, Reinhard Genzel, and Andrea Ghez, just won the Nobel Prize for their work on black holes. And two of those are astronomers who, for 3 decades, collected data that showed that at the center of our Milky Way galaxy, the galaxy that we live in, there is a massive black hole. What is a black hole? Black hole is so dense that even light cannot escape from a black hole. It's one of the most mysterious regions of the universe. And as somebody who works on galaxies, they play an immense role, because as gravity from black holes sucks in matter, that matter releases tremendous amount of energy. Sometimes that energy outshines 100 billion stars. What impact does that energy have on matter? How does it shape the future history of a galaxy forming? These are some of the questions that I work on. These are the puzzles. I do astrophysics because I am an intensely curious person. I want to understand how nature works, and somebody has decided to pay me to do this thing that I'm very passionate about. So for me, it's entirely a curiosity-driven endeavor. But society as a whole supports scientists because there is value in understanding the very laws of nature. We use our understanding of the laws of nature to innovate. Let me give you a simple example. 100 years ago, when Einstein was trying to understand gravity, people asked, why? We already know how gravity works. We can do calculation based on Newton's things. If you wanted to send a rocket to the moon, you wouldn't need Einstein's theory. So why worry about how gravity actually works when we can just do the calculations? Einstein wasn't happy with that. He actually wanted to understand how gravity worked. And in doing so, he found that the flow of time changes depending on where you are. The flow of time on a satellite, the speed at which clocks tick on a satellite is different from the way it ticks on the surface of the Earth. Again, you may say, why is that important? Your GPS would not work if you did not correct for the fact that these clocks run at different times. You could be going down the road and your GPS says turn left and you'd end up going over a cliff. Let me give you another example. When we are trying to understand universe, when we are trying to peer as far away and as far back in time as we can, we are looking through telescopes, and often the galaxies that we see are little smudges. How do we make sense of these little smudges? Astrophysicists and astronomers are amazingly creative people in terms of coming up with new ways of bringing out detail from digital images. And in doing that, we're not doing the science that we want, but we are creating new technology in order to do the science that we want. But that new technology then finds a home elsewhere. So think about a mammogram. When doctors take images of the breast tissue, because of the content of the breast tissue, very, very small cancer nodules disappear because they look like little smudges and they are hard to find. Using the digital magic that astrophysicists and astronomers have created, you can now pull out information about cancer nodules that are as small as a millimeter and smaller still. So I was born in Tanzania. I grew up in Mwanza for the first 10 years of my life. I was always an intensely curious kid. I was one of those kids that after a rainstorm, when a pothole filled up with water, I would squat by the pothole and watch little insects bounce around. I would look at the sky and ask not why are there constellations up there, but why do you see this fuzzy thing in the sky that later on we discovered is one of the nearest galaxies to our own, the Large Magellanic Cloud and the Small Magellanic Clouds. I was one of those people who looked up at the sky and asked, why is that star red and the other one white? My parents indulged me. When I squatted by a pothole to look at the insects, my mom did not rush me along. She actually stood there. Sometimes she would squat with me. She would point out the little things that were happening in that little puddle. Same with the stars. I remember lying on the beach in Upanga when I was 4 or 5 years old. My mother and her sisters were all involved in the Girl Guides in their youths. They knew about the stars. We would lie there, they would point out the constellations to me. And they continuously encouraged me to ask questions. They continuously encouraged me to remain curious. And they literally promoted my passion. So at no point did I feel the pressure to become a doctor just because I was good in sciences. 30 years ago, when I was going through graduate school, one would have said that the the range of opportunities were rather narrow, and that more often than not, people became academics, researchers. That's not true today. Today, the landscape of opportunities is wide open. With the skills that an astrophysicist has, we are able to do not just computing, we have facility with advanced computing. We have a facility with advanced mathematics. We are creative in our thinking, we think out of the box. We don't look for answers that already exist. We're actually looking for answers that do not exist. We are not afraid of coming up against hard problems. We have these skills and this tenacity, if you will, that's trained into us to solve some of the hardest problems in the world. And so, today, astrophysicists, physicists, they're all in very high demand by companies like Facebook and Google and Microsoft and 100 startups that are working with data science.
It was so interesting to learn that as gravity from the black holes suck its matter, it releases tremendous amount of energy. I am too sure it was as interesting for you as well. Our next guest is Hassan Changani, a software developer at Oasis Loss Modeling Framework, where he's helping build an open source catastrophe modeling platform. Prior to his current position, he was an academic astroparticle physicist for last 10 years after achieving his PhD from the University of Sheffield. Over his academic career, he has worked in United Kingdom, Slovenia and United States for the variety of particle physics projects, specializing in dictator physics. The majority of his career has been dedicated to the search of dark matter, a hypothetical particle that may account to the loss of the missing mass of the universe.
My name is Hassan Giugani. I'm from the United Kingdom and I am a software developer. I wasn't always a software developer. I was actually an academic physicist. I studied my PhD at the University of Sheffield. I got that about 12 years ago, and since then I've been working in academic physics for about 10 years. And I made the change to software development about 2 years ago. I was attracted to physics in school. It was one of the few subjects that I studied where I could actually see what I was learning in the laboratory, and that was very exciting to actually see, to actually build the circuits and to actually see that, oh, this is how current flows. So I spent most of my time as a particle physicist, particle astrophysicist, and most of my research was on dark matter. So dark matter is the missing mass of the universe. So you, me, the camera that you're looking at me through, the stars, the planets, the chair that I'm sitting on. All of this stuff is visible matter, baryonic matter we call it. And we believe this makes up 5% of the universe. And what I was doing was to try to find out what the rest of the universe was made out of. And we think that about a quarter of this is something called dark matter, which is something really bizarre. It just passes straight through us. So we're literally in a sea of dark matter at the moment. And it was actually trying to detect that and trying to find new detection techniques for something that really doesn't want to interact with matter, doesn't want to be detected. Dark matter itself is a very difficult material to detect. Of course, we haven't yet detected it. It doesn't want to interact with anything. And what I mean by that is that let's say that you have your detector, and the way that you tell if a particle has come into your detector is that it actually interacts and gives you a signal. And dark matter, seeing as it just passes straight through us, just doesn't interact with the detector. So we have to do certain things to encourage dark matter to interact. But I don't really mean encourage, I mean discourage everything else from interacting. Because every time that we see another particle interacting with our detectors, we don't detect dark matter. So what we do is we do things like we go underground into mine shafts to get rid of the cosmic rays that we are getting at the surface here. We choose very radio pure materials. So for example, stainless steel is a very difficult material for us to work with because it's quite radioactive. A lot of that is to do with contaminants from disused nuclear warheads. Recycled nuclear warheads that have gone back into the contamination supply, which are perfectly fine for us. There's no need to worry about that. But for our detectors are so sensitive that they pick up this radioactive material. So we have to use things like copper and ultra pure copper, and we use shielding techniques such as ancient lead. So we actually get lead from shipwrecks. So from actual shipwrecks, Roman ships that have gone down in the Mediterranean, and we actually like take lead from there and put it around our experiment. So this is like antique lead, purely because that lead has been underneath the ocean for thousands of years, underneath the Mediterranean Sea, and it simply doesn't have the amount of cosmic ray damage that regular lead that we have on the surface has. And we have to be very careful with our detectors. Like every single testing bit we do with our detectors on the surface, we are basically irradiating our detectors with cosmic rays, so that when we go underground, we are seeing that as well in our detectors. So we have to minimize the amount of time that we spend testing our detectors on the surface as well. So as a physicist, I had to analyze a lot of my data. And so the way that we would actually analyze, you may analyze at school using Excel, but we would actually analyze by programming. So we would have a framework that would provide us with the ability to use graphs, use plots, take statistics from our data, and we'd actually write C++ programs to do that. And later on in my career, we shifted from C++, which is actually it's a high-level language, but it's rather difficult, to something a bit more intuitive like Python. So basically, I was in that shift from C++, which is kind of still used, to Python. And the fact that I was exposed to these two languages, and these two languages are the languages that I currently use in my profession. That's how physics actually helped me in my job. My mother was very supportive of my decision to pursue physics at degree level and to follow in and do research. Probably because she was a scientist herself. She had a chemistry degree from the University of Karachi. So I had a lot of encouragement from her as well, to do what I felt passionate about. So for anyone wanting to enter software development, I would advise them to get stuck in. Not to just follow a course blindly. You can look at many courses online, like learning Python, learning Java, learning C++. You can find these courses online. It's a fantastic resource, and you should certainly go and take a look. But as you learn, you should also be practicing what you learn. So you should also be trying to think about projects that you want to build and starting to build them, and make changes as you learn new things about the programming language that you select. And you should only select one programming language to start with. Don't select a plethora of them. One way to get into this is to actually get yourself a Raspberry Pi, which is a small computer. And you can plug that into a keyboard, into a monitor, and you can actually start programming on it. By pursuing a degree in physics and astrophysics, you're not only open to a career in doing research or in teaching, and those are noble fields to go into, but the degree arms you with the ability to think. It gives you problem-solving skills. It develops those skills, and those skills are highly valued in other fields, such as the field that I'm involved in, such as in programming, but also in other fields such as consultancy and in finance. But myself, you shouldn't think about physics as being something that you do and end up in physics only. Myself, I did physics, and I even did it to PhD level, and I ended up as a software developer. What happened when I left physics, and how I became a software developer. So of course I had the programming experience, but I left my job. My contract came to an end. I left my job, and I had saved up enough money that I could take a few months to actually really sit at home and program every day and build applications. and try to build up my skills that way and kind of build a portfolio in order to get another job. So this was, of course, a difficult time. You know, I had planned for it, but of course, it's starting another career. So basically, you're going to hit the job rejections again because you don't have any history in that career. And it's just like coming out of university and trying to get your first job. And that first job is the hardest job to get. But once you've got it, then you've got your foot in the door, and you can rise up the ranks. So I would advise any budding physicists to actually ask questions. And ask lots and lots of questions. You know, why is the world in the shape that it currently is? You know, and these could be very mundane questions. You know, such as why is it that when I put a book on a table, the book just doesn't simply sink into the table? What is actually preventing that book from sinking into the table? You know, why is it that when I turn on a light switch, does the bulb actually come on? And if you keep asking yourself these questions, and if you keep looking for the answers, this is really where the beauty of physics lies. It is essentially describing the world around us and our understanding of the world around us. And the fantastic thing about it is that day by day, our understanding of that world changes. And by studying physics and by asking these questions, you are essentially doing what the scientists do every day of their lives.
It was very interesting to know that 25% of our universe is made up of dark matter, wasn't it? Medieval Islamic astronomers contributed to extended mankind's sign beyond our solar system. Al-Biruni and Al-Tusi were the first one to describe about the faint white ribbon that stretches over the night sky. That ribbon is our galaxy, the Milky Way, which is made up of hundreds and billions of stars, including our sun. Al-Sufi is also credited for the first recorded observation of two galaxies beyond Milky Way, the Large Magellanic Cloud and Andromeda Galaxy. This brings us to our next segment of Islam and Science.
Scholars from early Muslim societies and civilizations made significant contributions to the field of astronomy. This can be seen by the number of texts, instruments, and material culture that they produced. So great was their influence that remnants of their observations and theories can still be found in astronomical discourse today. A significant number of stars in the sky, such as the Aldebaran and Altair, or astronomical terms such as Alidade, Azimuth, and Nadir, are Arabic in origin. Astronomy, as understood and studied today, was different in the pre-modern Muslim world. It included folk astronomy, astrology, natural philosophy, and mathematical astronomy, each with a distinct subject matter and methodology. Since a number of Islamic rituals are closely connected to the movement of cosmic bodies, the study of astronomy proved useful for Muslim scholars in a number of ways. Astronomy provided methods for calculating the Qibla, methods to calculate daily prayer times, and methods for establishing the beginning of months, including Ramadan, all of which depended upon the movement and visibility of celestial bodies. Although the initial impetus to better understand the cosmos may have arisen out of necessity to fulfill religious obligations, what the scholars discovered and documented went well beyond. The translation movement introduced Greek and Sanskrit astronomical traditions into Muslim civilizations. Astronomers mastered the ancient Greek Ptolemaic planetary models and improved computational and observational techniques. They also enhanced existing instruments such as the astrolabe, important for celestial measurements and navigation, and established large-scale observatories. But most importantly, some astronomers were critical of the planetary models transmitted to them by their predecessors. In keeping with what is referred to today as the scientific method, scientists such as al-Battani and Ibn al-Haytham questioned the predictive ability of existing theoretical models, when their own observations yielded alternative results. Al-Battani and Al-Biruni, for example, studied and improved upon some of Ptolemy's results, incorporating newer and more precise measurements. Al-Battani compiled new astronomical tables of the sun and the moon, long accepted as authoritative. Ibn al-Haytham took it one step further. He highlighted the inherent contradictions in Ptolemy's works and proceeded to provide a geometric description that could explain the observed motions without the contradictions inherent in Ptolemy's model. Their contributions had an important influence on scientists such as Copernicus, Galileo, and Kepler, which in turn have an effect on how we understand astronomy and astrophysics today.
Our next segment is on exciting weekly rundown of global news on emerging science, technology, and other extraordinary advancements.
Scientists have devised a way to use a brain implant to stimulate the visual cortex to produce a relatively clear and functional kind of bionic vision. Dynamic current steering involves tracing shapes with electricity onto the brain's surface. The Orion system uses an eyeglass-mounted video camera to send information to an electrode array on top of the brain's visual cortex. It is currently limited in resolution due to engineering limitations. 6 patients have received the implant so far, and it has allowed them to see letters as they are drawn. Drone use in agriculture is expanding in China faster than in other countries due to advances in autonomous navigation technology and the presence of competent operators. Boasts that it has 42,000 drones flying over 1.2 million flights every day. Drones are more efficient and cheaper than skilled manpower while also being environmentally friendly. They enable older farmers to continue to work. Farmers are becoming proficient drone pilots as they monitor their crops, distribute seeds, and fertilize more efficiently. Imagine tiny devices, nanorobot or nanomachines that are as small as a billionth of a meter in size, which can be injected into our bodies to break down clots in our arteries, identify and destroy cancer cells, or assemble highly efficient, next-generation memory and logic circuits. This is an emerging field, but there are a number of problems to overcome, one of which is how to power these tiny devices. Astronomers have discovered a rare molecule in the clouds of Venus. Phosphine is a smelly toxic gas that, on Earth, is made by industrial activity or anaerobic microbes, typically found in places like sewage, swamps, and the intestinal tracts of animals, from penguins to people. It is also very easy to destroy by sunlight and sulfuric acid, both of which are in ample supply on Venus. So if the gas was produced a long time ago, it shouldn't still be detectable. The fact that it has been detected means that its production must be ongoing. Astronomers have long speculated that the clouds of Venus could be home to free-floating microbes. The detection of phosphine may well portend the existence of extraterrestrial aerial life. Engineers have developed a white paint that can keep surfaces up to 18 degrees Fahrenheit cooler than their ambient surroundings. The paint reflects 95.5% of sunlight and efficiently radiates infrared heat. It reflects heat back into the universe, which is an infinite heat sink. The paint could one day be used to combat global warming and is so good that it could replace the need for air conditioning.
Let's hear what Maulana Hazar Imam has said about creation.
But in Islamic thought, as in this building, beauty and mystery are not separated from intellect. In fact, the reverse is true. As we use our intellect to gain new knowledge about creation, we come to see even more profoundly the depth and breadth of its mysteries. We explore unknown regions beneath the seas and in outer space. We reach back over hundreds of millions of years in time. And the more we discover, the more we know, the more we penetrate just below the surface of our normal lives, the more our imagination staggers. Just think, for example, what might lie below the surfaces of celestial bodies all across the far-flung reaches of our universe. What we feel, even as we learn, is an ever-renewed sense of wonder, indeed, a powerful sense of awe and of divine inspiration.
Thank you again for watching this week.